Good morning everyone. So in the last classes we have seen about different types of DC to DC converters, that is buck converter, boost converter, buck boost converters. So today we are going to discuss about isolated DC-DC converters. Okay. So if isolated DC-DC converter is there, means there will be non-isolated DC-DC converter. So what is the major difference between the isolated DC converters and non-isolated DC converters? So first we can see about isolated DC converters. So isolated power converters or isolated DC converters isolates the input and output by electrically and physically separating the circuit into two sections, preventing direct flow of current between the input and output. Okay, so that is the main thing. That is, isolated power converters isolates the input and output electrically and physically, typically by using a transformer, so that there is no direct flow of current from input to output. Okay, so that is a major difference. അതായത് ഐസൊലേറ്റഡ് കൺവേർട്ടേഴ്സിൽ ഇൻപുട്ടും ഔട്ട്പുട്ടും സെപ്പറേറ്റ് സെക്ഷൻ ആയിട്ട് വെച്ചിരിക്കുകയാണ്. There is no direct flow of current from input to output. Okay, so these kinds of DC-DC converters are called as isolated DC-DC converters. The separation between the input and output typically is achieved by using a transformer. മെയിൻലി ആ സെപ്പറേഷൻ പറഞ്ഞല്ലോ, ഇൻപുട്ടും ഔട്ട്പുട്ടും തമ്മിലുള്ള സെപ്പറേഷൻ, അത് നോർമലി വരിക ട്രാൻസ്ഫോമർ വെച്ചാണ് അത് സെപ്പറേറ്റ് ചെയ്യുന്നത്. അതായത് ട്രാൻസ്ഫോമറിൽ എങ്ങനെയാണ് അതിൻ്റെ ഫ്ലോ വരുന്നത്, അതിൻ്റെ ഇൻഡക്റ്റൻസ് വെച്ചിട്ട്, മാഗ്നറ്റൈസിങ് ഇൻഡക്റ്റൻസ് വെച്ചാണ് ഇൻപുട്ടിൽ നിന്ന് ഔട്ട്പുട്ടിലേക്ക് എനർജി ട്രാൻസ്ഫർ ചെയ്യുന്നത്. ഓക്കെ, whereas a non-isolated power converter has a single circuit in which current flow between input and output directly. In the case of non-isolated converter, that is the major difference. In the case of non-isolated DC-DC power converter has a single circuit in which current can flow from input to output directly. Okay, so buck converter, boost converter, buck boost converter, all are non-isolated DC-DC converter. We have seen all these converters. It is a single circuit. There is a direct flow of current from input side V into V out. Okay, there is no physical or electrical separation. So buck converter, boost converter, buck boost converter, which all converters we have studied already, are non-isolated DC-DC converter. So here we are going to study isolated DC-DC converter. In isolated DC-DC converters, the input and output is isolated physically and electrically, typically by using a transformer. So the different types of isolated DC-DC converters are: one is flyback converter, forward converter, push-pull converter, half bridge converter, full bridge converter. So these are the different types of isolated DC-DC converter: flyback converter, forward converter, push-pull converter, half bridge converter, and full bridge converter. Okay, so we will be studying one by one. So first one is flyback converter. It is one of the type of isolated DC-DC converter. So in the case of flyback converter, it is mainly used with application with less than 100 watt capacity. Watt is somewhat less, capacity is somewhat less in the case of flyback converter. Maximum it will be having a 100 watt capacity. So here the energy transfer is heavily depending on magnetizing inductance of the transformer. I have told you that here in the case of isolated converter, there will be a physical and electrical separation between the input side and output side. So here in most of the cases we will be using transformer as the separating element. Okay, so here in the case of flyback converter, it is depending on the magnetizing inductance of the transformer for the energy transfer from the input side to output side. The high frequency transformer used in flyback converter, its magnetizing inductance is the source of energy transfer mechanism. That is what I told you. The high frequency transformer used in the case of flyback converter for that electrical and physical separation is the, and it will be having magnetizing inductance. That magnetizing inductance is the major source of energy transfer in flyback converter. Already I told the capacity is in between 50 watt to 100 watt. Capacity is very less in the case of flyback converter. So it is also a developed buck boost converter. Okay, we will see that. Okay, so this is the circuit diagram of the flyback converter. Here input side, input is there, then a transformer primary winding is there with N1 turns. Okay, this is the primary winding. Switch is placed here in this input side. Then in the output side, means secondary side, the transformer N2. Okay, secondary winding is there, N2, which with the number of turns is N2, and the remaining is same as what we have seen in buck boost converter. A freewheeling diode is there. Instead of inductor will be here internally present, then freewheeling diode is there, then capacitance is there, then the output is taken here. Okay, so this is the circuit of flyback converter. This side, this secondary side, you can see it will be resembling like a buck boost converter. So it can also also called as a modified buck boost converter. A buck boost converter which is isolated, non isolated, then it is a flyback converter. Okay, so this side is primary and this side is secondary. This is the input side and this is the output side. Switch is placed here in the input side. Here one major thing you can note here, that a dot is placed here in the primary side and a dot is placed here in the secondary side, and these dots are placed opposite to each other. What does it signifies? It signifies that the winding of the primary and the winding of the secondary will be of opposite direction. Okay, winding of the primary and the winding of the secondary will be of opposite direction. That is, here dot end is there, here also one dot end is there. Whatever the polarity is there in this dot end, it will be inducing that same polarity in this dot end. Okay, so it will be of means if you are seeing this figure, it will be of opposite direction. So if a plus is inducing here and a minus is inducing here, in this side also dotted end will be having plus polarity and the non-dotted end will be having minus polarity. So ultimately what will be happening, if a polarity of plus minus is inducing here, here it will be a polarity of minus plus. Okay, it will be of opposite polarity in this secondary side. Okay, so the flyback converter transfers energy by virtue of magnetizing inductance of the transformer, that we have already told. The dot represents that is of same polarity. Dot means that is of same polarity. That is, if a plus is inducing in this dot side and a minus is in minus polarity is there in this non-dot end, means in secondary side also plus polarity will be having in this dotted end and minus polarity will be having in this non-dotted end. Okay, so dot represents that same polarity in primary and secondary side of the transformer. The transformer used is ferrite core high frequency transformer. This transformer used here is a ferrite core high frequency transformer. Here the switch in primary side and the freewheeling diode in the secondary side are mutually exclusive. Okay, switch in the primary side and freewheeling diode in the secondary side are mutually exclusive. Means whenever the switch is on here, this freewheeling diode will be reverse biased. It will not conduct. And whenever this switch is off, the freewheeling diode here will conduct. Why it is so? Because I have told you that the winding of the primary and secondary is of opposite direction. So the polarity inducing here, when the switch is on here, it will be plus minus. Okay, when the switch is on here in this primary side, it will be this dotted end will be having plus and this not dotted end will be having minus polarity. So same polarity will be inducing here, that dotted end will be having plus and non-dotted end will be having minus. So here it is minus, and this minus is connected to freewheeling diode, which means it will be reverse biased. Okay, so the switch and freewheeling diode, in the case of flyback converter, it will be mutually exclusive. That is, whenever the switch is on, freewheeling diode will not conduct, and whenever the switch is off, the freewheeling diode will conduct. Okay, when the switch is on, diode is reverse bias, and when the switch is off, diode will be forward bias. So mode 1, when the switch is on, so the equivalent circuit will be coming as like this. I have told you, when the switch is on, this dotted end will be having positive polarity and non-dotted end will be having negative polarity. Same it will be inducing in the secondary side. Dotted end will be having plus polarity, non-dotted end will be having minus polarity. As the result, this diode, freewheeling diode, will be reverse bias. Okay, freewheeling diode will be reverse bias, and the capacitor, which will be already charged, it will be delivering power to the load. Okay, so when the switch is on, the polarity is on as in figure, in the primary and secondary windings. Current path in primary side will be like Vi, then this primary switch, again Vi. Okay, this will be the current path. So the energy stored, the voltage across the primary side, we can written as Lm into delta ILm. Okay, Lm into delta ILm means it is the rate of change of voltage in this primary side, Lm into delta ILm, which is equal to Vi into dt. This is for on time na. So Vi input side into dt. Okay, Vi into dt. Okay, so this delta ILm will be the increasing current, as the inductor will be charging at that time when the switch is on. So Lm is the magnetizing inductance, delta ILm is the rate of rise of current, inductor charges at that time, and dt is the on time. Dt is the on time, and Vi is the input voltage. Vi is the input. So this is the equation number 1. When the switch is on, freewheeling diode in the secondary side is reverse bias. Already told, freewheeling diode will be reverse bias, so it will be open circuited. Here the capacitor which we placed here, it will be delivering power to the load at that time when the switch is on. Okay, so now mode 2, when the switch is off. When switch is off, what will be happening here, the primary side, it will be reversing the polarity. Okay, it will be reversing the polarity, that is non-dotted end will become plus and dotted end will become minus. Similarly, dotted end will be becoming minus here and non-dotted end will be becoming plus here. As the result of this plus polarity here, the diode will be conducting. Okay, so the inductor will be discharging its energy. Okay, inductor will be discharging its energy and it will be appearing across the load here. Okay, so when the switch is open or off, the charge inductor releases its energy. The inductor releases its energy, the polarity is reversed. The polarity across primary and secondary is shown in figure. As the polarity is reversed, the diode will conduct, so short circuited. As diode D conducts, output voltage will be equal to voltage across the secondary side. Voltage across the secondary side. So what will be the voltage across secondary side? Okay, so it will be Lm into delta ILm, which is equal to, this is the secondary side, Lm into delta ILm, which is equal to voltage across the secondary side when we are looking from primary side is V0 into N1 divided by N2 into 1 minus D into T. This is for when the switch is off, which is 1 minus D into T. Okay, this is the off time, 1 minus D into T. T off means 1 minus D into T. We have already seen in buck boost, buck converter, boost converter. Okay, how it is coming. Okay, so Lm into delta ILm, which is equal to V0 into N1 by N2. This is the voltage across the secondary side into 1 minus D into T. 1 minus D into T means T off. T off we can written as 1 minus D into T. Okay, so this is the equation number 2. Here the delta ILm. Delta ILm means rate of decreasing of inductor current. Because in this case, as the switch is open, the inductor which is already charged, it will be discharging its energy. So it will be a rate of decreasing current. Okay, inductor discharges. And 1 minus D into T, which is the off time, T off. And N1 is the number of turns across primary and N2 is the number of turns across secondary. Okay, so this is the secondary voltage. V0 into N1 divided by N2. Okay. Okay, understood. So this is the equation number 2. So equating equation number 1 and equation number 2, we will get V0 and N1 by N2 into 1 minus d into t, which is equal to Vi into dt. dt cancel. Finally, we will get V0 by Vi, which will be equal to d divided by 1 minus d into N2 divided by N1. So this is the relation between the output voltage and input voltage. So here we can see it is depending on the duty cycle as well as the number of turns across primary and secondary. That is V0 by Vi is equal to d divided by 1 minus d into N2 by N1. So this is the relation between the output voltage and input voltage in case of flyback converter. So this is the waveform. This is the waveform. That is when the switch is on, the voltage across this switch will be 0. Okay, that is what shown here. The primary current, it will be increasing as the inductor is charging, so primary current will be increasing. Secondary side, no current will be there. Okay, because the polarity is opposite. The polarity will be opposite and the diode will be reverse bias, so no current will be there in the secondary side. Okay, diode is reverse bias now, so there is no current in the secondary side. And the secondary voltage, as I told, the primary polarity and secondary polarities of opposite directions. So primary will be having plus minus, so secondary will be having minus plus polarity. So the secondary will be having a negative voltage and the flux will be increasing. Okay, flux will be increasing from minimum to maximum when the switch is on. So now when the switch is off, we will be having across the switch, we will be having 2 Vi voltage, and here one spike will be there. This spike will be because of the inductor releasing its energy. Okay, so when the switch is off, there will be 2 Vi voltage. How 2 Vi voltage is coming, I will show. So when the switch is off, what will be happening? Already a Vi will be charged here. Okay, and also here input is Vi, so Vi charged here, it will be discharging. Okay, plus the already Vi is there, so across switch it will be plus Vi, which is discharging, plus already Vi input voltage is there, so across switch it will be 2 Vi voltage, and the spike I have shown there, it is because of that the presence of inductor. Okay, so during off time, the voltage across the switch will be 2 Vi. How that 2 Vi is coming? Already one Vi is there, and also inductor will be charged with Vi. So Vi plus Vi, it will be 2 Vi across the switch. Okay, switch will be having 2 Vi voltage, and also primary side, now no current is there as the switch is open, and the secondary side, we can see the inductor is discharging, so it will be a decreasing current. Here it is increasing current as the in the primary side as the inductor is charging. In the secondary side, the diode is forward bias now, and also the inductor is discharging, so inductor will be discharging from maximum to minimum value. Okay, and also in the secondary side, now the polarity is reversed, that is dotted end will be having minus polarity and non-dotted end will be having plus polarity. So ultimately the polarity across the secondary will be like plus minus, diode will be conducting. So in the secondary side we will be having a plus V voltage. Okay, and the flux will be decreasing here. So that is what the graph shown here. So when the switch is on, across switch there will be 0 voltage. Okay, the primary voltage, it will be so the primary current, it will be increasing as the inductor is charging, so it will be increasing from minimum to maximum. In secondary side, no current will be there as the diode is reverse bias, and the secondary voltage across secondary will be minus volt as the polarity is reversed due to the difference in winding. and the flux will be increasing from minimum to maximum. And when the switch is off, the voltage across the switch will be Vi plus Vi, that is 2 Vi, and the spike is due to the presence of that inductor. And in primary side, no current will be flowing as the switch is open circuited, and in secondary side, the diode is forward bias. As a result, current will be flowing there, and the current will be decreasing there as the inductor is discharging. So inductor will be discharging from maximum to minimum. Okay, and as the polarity is reversed, non-dot end will be having minus polarity, and the dot end dot end will be having minus polarity, and non-dot end will be having plus polarity. As a result, in secondary side we will be getting a positive voltage, and the flux will be reducing from maximum to minimum. So that is about waveform. That is what I have written here. Here it is divided as mode 1, mode 2, mode 1, mode 2. Okay, mode 1 means which is on, primary current increases from minimum to maximum, secondary current is 0, voltage at output side will be negative, flux will be increasing gradually. In mode 2, switch is off, voltage across switch will be 2 Vi, also little spike due to the inductance, and primary current is 0, secondary current will be decreasing from maximum to minimum, output voltage is positive, flux will be gradually decreasing. This is what I told before, same thing only. And the major advantage of this flyback converter is capacitor size is less in continuous conduction mode. That is the capacitor used here, that size is less in continuous conduction mode, and also peak current rating of this flyback converter will be less. And the disadvantages of this flyback converter need a fast diode. The diode, freewheeling diode which we used here, it should be a fast diode. Freewheeling diode should be a fast diode. Okay. And the large size of transformer, that is also another disadvantage. Here the transformer we used, it should be of large size, but the output we are getting here, it will be of maximum of 50 watt to 100 watt. So for a less output we are having a large transformer, so large amount of copper loss will be there if we are using that large transformer. So a large size transformer is used, but we are getting a less output also. So because of that, large copper loss will happen in case of flyback converter. Okay, and also additional filter is required in continuous conduction mode for filtering out DC. If more leakage is there in flux in the case of flyback converter, it will not work properly. So in the transformer side, if more leakage is there in flux, the flyback converter will not work properly. And also here the primary current and secondary current is not continuous, that we have seen in waveform. Primary current, this is the primary current, it is not continuous. That is when the switch is on, the inductor will be charging from minimum to maximum, and when the switch is off, there is zero current. Similarly, in the case of secondary, when the switch is on, the diode will be reverse bias. As a result, no current is there across secondary, and when the switch is off, diode is forward bias. So because of the inductor discharging, current will be decreasing from maximum to minimum. Okay, so these all are the disadvantages of flyback converter. So in the next lecture we will be discussing about forward converter. Okay.